Okay, the next topic is multivariate calculus. So the reason why we are studying this part is because usually our estimation involves some kind of minimization or maximization. So let's just do some examples. For example, so we all know already that the OLS, the objective function that we want to minimize for our OLS estimation has this this form. So our Q of beta equals to y minus x beta prime y minus x beta. Okay, and this is y prime y minus beta prime x prime y minus y prime x beta plus beta prime x beta. So y here is n by 1 vector, and x here is n by k dimensional matrix, and beta here is k by 1 vector. So what you can see here is this is a scalar, and this is a scalar, this is a scalar, this is a scalar. So our Q function Q maps our K space to R. Okay. And since here this and this are scalars, so we can simply and since y prime y does not have any beta, we can rewrite this function as a constant minus 2 beta prime x prime y plus beta prime x beta. Okay. So we want to find the minimum as you see, you already know minimization. Since this is a continuous function, minimization involves the first order derivative being 0. So at our beta hat, the optimizer, minimizer, or OLS estimator, we know partial Q beta hat at partial beta is 0. What do I mean by this notation? To simplify, let's just use a simple case. K is 2. When K is 2, it has the following structure. So minus 2 beta 1 beta 2 prime, and x prime y is so x prime y, or Q of beta 1 beta 2 is plus beta 1 beta 2 prime x beta, which is beta 1 beta 2, and this here is what k by 1 dimension, and this here is k by k dimension. So let's use some simpler notation, which is minus 2 beta 1 beta 2 prime. Let's call this A, plus beta 1 beta 2 prime A beta 1 beta 2. So first let's think about partial beta and beta 1 beta 2 prime A. Okay, so here A you may write as A1 A2, and here this a you may write as a1, a2, a2, a3. Okay, this notation is a simpler form of the following: partial beta 1, partial beta 2. So it's as if notation wise it's as partial beta 1, beta 2. And we are dealing with a scalar function, a vector derivative of a scalar function. So this maps R to R squared. Okay. And the working of this one is this: partial some function partial beta 1, partial some function, not this one, sorry, partial beta 2. We are going to write this one as if it's just a vector. So it's a definition. And let's do the first element. Partial function. Here our function is this, right? Partial beta 1, beta 2 prime a over partial beta 1, which is partial beta 1 beta 1 a1 plus beta 2 a2, because we are talking about this, which is a1, right? And what about the other one? Partial beta 1 beta 2 prime a over partial beta 2. You can see that this has to be a2. Therefore partial beta 1 beta 2, or let's change notation now. Here we are talking about beta prime a is a1 a2, which is a, right? Which is a. Now you can do the same thing to see that partial beta prime a beta is a beta. Okay, so derive this one. So eventually what you get here is partial beta q of beta is minus 2 partial beta prime a plus partial beta prime a beta, which is minus 2a plus, oh sorry, I meant 2. Let's make it clear. This actually is a beta plus a prime beta, but in our case a is symmetric, so this is going to be 2a beta. So plus 2a beta, and what we know here is at the beta hat, the first law condition means at the beta hat it has to be 0. Therefore beta hat is a inverse a, which is x prime x inverse x prime y. Okay, so that's how you do the multivariate calculus. The second order derivative is this. Here partial beta Q of beta is a k by 1 vector. So to do the second order derivative, we do this partial beta prime partial beta q beta. Okay, and this is k by 1 vector, this is 1 by k, the other way, sorry. So the second order derivative of vector valued function, the vector multivariate function is here and here. So this is partial beta q of beta prime. So it's like partial beta 1 q of beta, partial beta 2 q of beta. Okay, so this is 1 by k vector, and this is k by 1 vector operator, so you get k by k matrix. Okay, so how do you what's the definition of this this derivative? It's this partial beta, and this here is 1 by k vector, so you have partial beta 1 q of beta, partial beta 2 q of beta, and the k by 1 operator is partial beta 1, partial beta 2. You do this as if you do matrix multiplication, and you get this partial beta 1, partial beta 1 q of beta, partial beta 1, partial beta 2 q of beta, partial beta 2, partial beta 1 q of beta, partial beta 2, partial beta 2 q of beta. Okay, and more familiar in a more familiar notation, we have partial squared beta 1 squared q of beta, partial squared beta 1 beta 2 q of beta, and partial squared beta 2 beta 1 q of beta, partial squared beta 2 squared q of beta. Okay, so do this and verify that this is 2 times x prime x. Okay, and notation wise, here instead of this, we write partial squared partial beta prime q of beta. So that's the Hessian. There's this mean value theorem, and you can read the matrix calculus formula that I want you to prove or verify. There is this Taylor expansion of multivariate functions. So f of q of beta, so q of beta, let's say q of beta is not necessarily a quadratic form, can be Taylor expanded to Q of beta naught at a naught at beta naught at the vicinity of beta naught plus beta minus beta naught prime partial Q partial beta some bar plus beta minus beta naught prime partial Q squared partial beta prime beta bar beta minus beta naught for some beta bar near in between beta and beta naught. Okay, when beta and beta naught are very close to each other, then Q of beta is approximated by Q of beta naught plus beta minus beta naught prime partial Q of beta naught over partial beta plus beta minus beta naught prime partial Q of beta naught partial squared partial beta prime beta minus beta naught. Okay, from here you can think about an algorithm that you can find the minimum numerically. Okay, and that's this. So your beta s equals to s plus 1 equals to beta s minus partial squared Q of beta s partial beta prime inverse partial Q of beta s partial beta. Now compare this with the algorithm for a univariate function. The algorithm for a univariate function, when you want to find the minimum or maximum, is this: beta s plus 1 is beta s minus partial d squared d Q of beta s d beta over d squared Q of beta at s over d beta squared. So this is the vector and matrix version of this algorithm. Okay, this lecture is quite short, and I'm gonna stop it here. I'll continue with probability theory and mathematical statistics next lecture.